12.2. Today we're going to look at evaluating limits algebraically, whereas 12.1 we looked at this graphically. And so before we begin looking algebraically, let's review how we did this graphically. What I'm going to do is estimate these limits, and to do so I'm going to use the calculator Desmos. So what I'm going to do is come over here to our digital classroom, and you can open up lesson 12.2. And when we're opening up 12.2, I'm just going to go to the pre-programmed graphs. Now today I'm also going to end up using a little page of notes as we go, just so you can see some rules. So I'm going to open that up. Not that you have to open up the digital note copy, but I will leave that open here in a second. And now I'm going to click on the pre-programmed calculators here. And specifically, I'm just going to open up for these limits. I'm just going to graph these functions as is, and so I don't need any special calculator. Each one of these is just a normal equation we could call f of x equals x squared minus 7x plus 9. That's what I'm going to graph here, and so on down here. That's a rational. We have an absolute value with a rational function, so there's nothing special here to graph. I don't need to do any special programming, so let me just open up a blank Desmos calculator, so we can estimate these in particular limits. I'm going to call this f of x, g of x, h of x. So if we ever load up here, okay, finally, here we go. We're going to say f of x equals x squared minus 7x plus 9. I'm going to use that graph first. Secondly, I will use g of x equals the rational function x squared minus 2x minus 24 all over x minus 6. And then I'm going to turn that off because that'll be number 3. And then we'll have this, number 2. We'll have h of x here equals the absolute value. Well, there's going to be a division and then absolute value. I'm going to go to Desmos Tools. So I'm not sure exactly what you type in for absolute value. X plus 2 over x plus 2. And that'll be for number 3. Okay, so for number 2, number 1 is not only do we look at this graph, typically we can use a table to help us out. And so when I'm looking at number 1, I want to estimate this limit as it approaches 4. So I can hit the edit and hit the table right here. And what's going to happen is it's going to give me these values. I want to approach number 4. So I'll do like a 3.9 here, 3.99, 3.999. I'll go ahead and type in 4. 4.1. Let me actually go smaller. Let's do 2 zeros, 1. 4.10, then a 1, and then 4.1. And you can kind of get an idea of what's happening to those values. As you can see, as we approach 4 from the left side, the values just to the left of x equals 4 here, as we approach from the left and as we approach from the right, we can see that we get closer and closer to the y value of -3. And so that's what the graph is approaching here. As the graph approaches, we're getting closer and closer to -3. If that makes sense to you. So this graph, the answer would be -3. Now let's try number 2. So number 2, we're looking at this limit, and when I graph this function, let me take off number 1 here, I'm going to go ahead and add a table. And we're trying to approach the number 6, so this time I'll have 5.9, 5.99, and a 5.999, just like I kind of did earlier, but with the 3's. And then there's the number 6, and then we'll have 6.001, 6.01, and 6.1. So now we can see as we approach from the left and as we approach from the right, it looks like it's approaching the number 10, even though this says it's undefined. So why is it undefined? What that means is that if you remember, you're not allowed to divide by 0. That's a mathematical rule. We cannot divide by 0. It's undefined. Thus, the table says undefined. But as you get closer and closer to 6, as you see this graph approaches it from the left, it's approaching that number 6 there. So as we get to 6, our function is undefined. It's the same going from the right. As we go from the right and approach from the right towards the left like this, from the right side, you'll see that when we get to 6, we are undefined. Thus, even though the function is undefined at the value 6, even though the function is undefined, the graph itself is, or the limit is not undefined. The limit approaches the value 10. So here, if g of x equaled x squared minus 2x minus 24 over x minus 6, g of x itself, or g of 6 itself, is undefined. But that does not mean the limit is undefined. The limit still exists because it's approaching the value 10. Okay, and now we have one more. Estimate this limit. And now, so you might notice that the symbols are a little bit different on number 3. It says -2 with a plus. That means from the right side, you're looking at the right piece as it approaches -2. So when I jump down to number 3 here, we're looking as the right piece approaches -2. What value would that approach? Well, on this picture it says undefined here, but our graph is not, or let me pull this up. So as we approach -2, let's say -2 point, no, never go to, I'm sorry, 1. No, that's right, because it's negatives, I need to go the other way. So -2.1, then -2.01, -2.001, and then a -2, and then we'll have -1.999, -1.99, and -1.9 like this. And you can see the values as it approaches. It doesn't seem to be defined at -2, or it isn't. The function itself is not defined at -2. However, its limit does exist on the right side. The right side limit would be the value y equals 1. That's the right side. As we come from the right to the left, the value is, the y value is approaching, would be +1. Now conversely, if you needed to know what's the limit, and I'm going to call this h of x just for short, the limit of h of x from the left side limit would be -1, which means the limit as x approaches -2 of h of x does not exist. Now, why does the overall limit not exist by review? Because the left side and the right side do not equal one another. Limit of hx from the left side does not equal the limit of h of x. That's an ugly h. Let me try that again. H of x from the right side. Since those do not equal one another, the limit itself would not exist, but this is just asking for the right-hand limit. The right-hand limit does exist. It is the value 1. Look at lesson 12.2 now. If you need this, if you want to pull up my calculators from Desmos, just go ahead and take a scan at that. Alright, so what we're going to look at today is evaluating limits of polynomial and rational functions, not only at selected points, but also at infinity. And so the terms you might hear today are direct substitution and indeterminate form. Actually, you probably won't hear me say that very often, but you will hear direct substitution quite a few times. So some limits of functions rules, as we've learned that if we're looking as x approaches this value c here, so as we approach c, that means you're looking at it as the graph itself approaches it from the left side and the right side. And if as long as it's the same value, we'd get the value k. And this is saying if you have a constant function, then the limit of x approaches c of k will be equal to that k. So if that's the y value, that's what it'll be equal to. And another one is also an identity function. If you're looking at the y equals x line, the line y equals x, or f of x equals x, if you're saying what's the limit as we approach this value c, well, the answer will be c, because the identity means the y is equal to the x. So if x is c, y will also be c. Now, here are the rules that, as I mentioned on the bell ringer, I'm going to leave up on this page. So if you remember, I went to our lesson instructions and I opened up the digital copy. You could also click the completed copy if you like. And I'm going to look for this particular slide, the property of limits, to keep that open as we go through today. So here's the property of limits, and I'm going to just zoom in on this a little bit. maybe even a little bit more, so we can see our properties as we go through today. So the whole idea today is, without using a calculator to graph like we did last class, how could we find the limit of this function? So looking on this, the graph, we would have said, okay, as we approach 3 from both the left side and the right side, it approaches the y value of 11. That's how we would have done this on lesson 12.1. Well, how can you do it on 12.2? Well, using these properties, first we could say that this right here would be equal to the limit of x approaching 3 of x squared plus the limit as x approaches 3 of 2x minus the limit of x approaching 3 of 4. Now notice I just kind of like distributed that limit through there, if you will. I put the minus on this side. You could have said plus a negative 4. It doesn't really matter. But I kind of distribute it through. Now that is using the sum property. So the property of a functions or multiple functions being added together, you could separate and do limits of each individual function and add those values up. That's what I did right there. That is the sum property. The sum property. Now as you look on, you will see that there's properties for if you have a power. So here's the power property. And it just says, hey, if you have a power, you can take the power of the entire limit. So using the power property, we could say this will be equal to the limit of the identity function as x approaches 3, and then just square this. That right there is what we call the power property. I'm just going to write power property. And then over here I have a limit of 2x. This is the scalar property. It says if you're multiplying a function, you can just move the scalar to the front. So I'll say this is the same thing as 2 times the limit as x approaches 3 of the identity function. That right there is the scalar multiple property, scalar multiple property. And then we finally have over on this side just that constant. If you remember from the previous slide, it's just a constant. And so that just means that the limit, no matter what the number is here, c, if it's a constant function, will be that a number here. So here I'm just going to, that was the limits of constant functions is what they call that. And so I'm just going to put minus 4. That's the limit of constant function. Limit of constant is what I'm going to write. Limit of constant. And so we just get the value 4 there. Constant. Okay. So now how do I evaluate this? Well, this right here is the identity function, which means that value is going to simply be 3 squared, because that's the limit of an identity function. Limit of identity function is just the number itself. So if x is approaching 3, that's a 3. So it'll be 3 squared. And put that squared more on the 3. Plus here, again, this is identity function. So it'll be 2 times 3 here, minus 4. And so those are both the limits of identity functions. So now I can just simplify the math. 3 squared is 9, plus 6, that's 15, minus 4 equals 11. And that is my limit right there. My limit as x approaches 3 of x squared plus 2x minus 4 would then equal 11. Using those properties. And so you saw it here graphically, and now doing algebra here. Here's part B. So it says use the properties of limits to evaluate this. And so I'm going to walk you through the same limits. So there is a quotient property, and I'm going to use that one first. It says the limit as x approaches negative 1 of 2x, there it goes, squared, minus 3. And the quotient property says is you would just separate it and have each limit individually. So I can take this limit and divide it up each individually. This is the quotient property. And now what I could do is separate these just like we did before. We could do the sum property. of 2x squared. I'm going to make that a minus the limit as x approaches -1 of, I took the minus already right here, so I'm just going to do a 3. All this over, that's the sum property, and I'll do the sum property down here as well. Okay, I'm going to put these in parentheses because that x and the plus look kind of strange to me. Let me put that in parentheses like that. Okay, so now I've used the sum property to distribute those out even a little bit further to separate them, simplify them. We could continue on this next one. I'm going to do true properties in 1. I'm going to change this right here to the limit as x approaches -1, and I'm going to put the 2 in the front. That's the scalar multiple property, and I'm also going to the x itself is squared, so it's not the 2 that's squared, just the x. I'm also going to square the limit itself, not the scalar, but the limit. And then I'll subtract this right here will become a 3. That's the constant function. Let me change colors, something I haven't used yet. This will be the scalar, constant. That's a limit of a constant. Over here, I forgot to write it. That was the scalar multiple. And the power property. And this will be divided by, over here, this is the identity function. So we'll have just a -1. That's the identity. A limit of an identity. What's the sign spell identity? I'm missing the, there we go. Limit of an identity plus 2, which would be a constant. So I'll color coordinate in here. And so now if I wanted to simplify this, I can go one more time. That identity function on the first limit will be, that value is a -1, so it'll be 2 times -1 squared. That's identity. And then we'll subtract the 3 over, and I'm just going to simplify this. -1 plus 2 is the same thing as 2 minus 1, which is 1. And so dividing anything by 1 doesn't change it. So it seems like to me that this value will end up being -1 squared, which is 1. 2 times 1 minus 3. Go ahead and put the equal sign right there. And 2 times 1 is 2 minus 3. I'm getting -1. So the limit of 2x squared minus 3 over x plus 2 as x approaches -1 will equal -1. And if you want to check this out by graph, you could. Let me clear off these. If I graphed 2x squared, make sure it's all dividing. Okay, 2x squared minus 3 over x plus 2. As we approach -1, you can see the y value that it's approaching is -1. As we approach from the right side and the left side, we approach -1. So we did in fact do that correctly. So let's try this one more time. Oops, let me get my properties back. Okay, and so now I have a root. And what this is saying is that you could say that this is equal to the square root of the limit as x approaches 2 of x plus 4. Now that right there is the nth root property. The nth root property gives us that. And now I can just keep using my properties from there. We have a sum property in there. So I could say the limit of x as x approaches 2 plus the limit as x approaches 2 of 4. And without just continuing to write the property names each time, I'll come back and do that in a second. This would be equal to, that right there will be 2. And this right here is 4. Identity, and that's a constant, which is going to equal the square root of 6. And so the answer here, since I cannot reduce the square root of 6, the limit as x approaches 2 of the square root of x plus 4 is going to equal the square root of 6. So now that I walked you through a few, you can go ahead and try this problem. Stop the video if you need to. Alright, so now how can we simplify our work? On this slide here, we see there's limits of function, and the idea is this: if p of x is a polynomial function and c is a real number, you could find your limit just by plugging in that value c in for your x, or substituting it in there to find your limit if it's a polynomial. And if it's a rational, you could do the same thing where you just plug in your value of c into the numerator, which we'll refer to as p of x, and to the denominator, which we'll refer to as q of x. There's one caveat to this, and it's that q of x, or if when you plug in your c value, your limit value, cannot equal 0, because in mathematics we're not allowed to divide by 0. So that's the one caveat here. You will have problems if you are trying to find your limit, but the denominator equals 0 when you substitute in. So this is just a direct substitution. So it's saying we can simplify all this problem using direct substitution. What they mean by that is we could say, okay, the limit, according to this slide, is going to be equal to just plugging in that number 2 all the way through. So we'll consider this our function p. And so p of 2, the limit of p of x, we'll call that, will equal p of 2. So I'm substituting in, I'm just using direct substitution where I substitute for every single x the value 2, because that's what we're saying x is approaching. Okay, so let's go simplify this. 2 to the 4th power, that's going to be 16. 2 times 2 is 4, times another 2 is 8, times one more 2 is 16. So it's negative 2 times 16, plus 3 times 2 cubed is 8. 2 times 2 times 2 is 8, plus 2 squared is 4, minus 2 times 2, which is minus 4, plus 5. We go to simplify. These two will simplify together, the 4's. And so negative 2 times 16 is negative 32, plus 3 times 8 is 24, plus 5. And so negative 32 plus 24 is negative 8, and 5, I get negative 3. Since p of 2 is negative 3, the limit as x approaches 2, I'm just going to call it p of x here, will equal negative 3 as well, because this is a polynomial function. Polynomial function is a function in terms of x where you have powers that are whole numbers, and not only that, they're positive whole numbers all the way across. You might say, well, this doesn't even have a power of x. Well, technically it is x to the 0. And so whole numbers, if you could say not just positive, but the whole numbers includes the number 0. So now let's look at the graph so we can see if we're correct. As we approach this value 2, right here, as this graph approaches the value 2, you can see the y value that it approaches is negative 3. So we did do it correctly. Much, much quicker using direct substitution than all the properties we had over here. So now this is a rational function. So I will kind of use, in one regard, the quotient property, which means I'm going to solve this, or we could call this right here p of x, and this q of x. And so basically what I want to try to find is p of negative 3, and then I'm going to divide that by q of negative 3. So let's see what these are equal to. So p of negative 3, if I plugged in the top, I'd have negative 3 squared plus 1. And in the denominator, I would have negative 3. And typically we use parentheses when we substitute, especially with the negative, minus 2 more. And so negative 3 squared is a positive 9. Negative 3 times negative 3 is a positive 9. I'll add 1 to that. Negative 3 minus 2 more would be negative 5. Think of a number line. If you're already on a number line, left 3 units, here's 0. If you're already left 3, 1, 2, 3. And you need to subtract 2 more. That takes you to negative 5. Or you can think of money. You owe someone $3, you owe someone else $2, you owe a total of $5. So that's our value there. Let's simplify this. 9 plus 1 is 10, divided by -5. I'm getting -2. That means the limit as x approaches -3, I'll just write out the actual equation here of x squared plus 1 over x minus 2 will equal -2. Again, we could check this in the calculator. Shouldn't take us too long. If we type this this equation in, x squared plus 1 over x minus 2. And we want to see as x approaches -3. As we approach -3, we're approaching the y value -2. As the x closes in on -3, the y value that's closing in on is -2. So that's how you kind of read this. It's kind of like what happens to the y value. That's the function represents this, all that equaled f of x, or y equals, typically we write that. So what's happening to this y value as x is approaching the -3? As we close in to the x value -3, what y value do we approach? -2. Here's one more. So let's use direct substitution. And so if I'm going to call this here p of x, notice this is, typically we don't think of this as polynomial, but if I want to try to use direct substitution, I'm going to see that this will be problematic. So our rules, if you've forgotten, our rules, by the way, are for polynomial and rational. This is not polynomial. Some would call that a power function, but it has the +3 with it. So this is just not polynomial. It's not a whole number power. It's kind of like the power of 1/2. So that's not truly even a polynomial. So I shouldn't call it p of x, but p usually being reserved for polynomial. Let's try this anyways. If I plug this in, I would be taking the square root of -4 plus 3. So this time we're going to run into problems, because when I add -4 plus 3, I owe someone $4. I have $3. When I add those up, I still owe $1 more. The square root of -1 we learned is equal to I, but I is imaginary. This is not possible. The square root of -1 is not real. We would just call that the imaginary number I. And so on this one, it would not be possible. All right, your turn to try to use direct substitution to evaluate this limit. If it's not possible, explain why. Pause the video if you need more time. All right, let's take a look now at example 3. Let's evaluate this limit. Well, here's one problem. If we try to use direct substitution, what would happen is I would substitute this 3 into the denominator, what we typically call q of x, and I'd have 3 minus 3 equals 0, and that would be a rule breaker. You're not allowed to divide by 0. So we have a problem. Well, one thing we can do is factor an equation. And so I'm going to factor the numerator here. It's a quadratic, which means I'm going to use x method, where I'm going to call this a, b, and c. Yes, we haven't gotten away from this. We started at the very beginning of the school year with x method factoring, and we're going to finish the year with it as well. That's right. I'll take my a times c and place it in the top of my x here. So 1 times -6 is -6, and b is -1. So I'm looking for two factors, which two numbers, we'll call it m and n, such that they multiply and their product is -6, and they add together and the sum is -1. The two numbers I'm finding here, the factors of 6 that have a difference of 1 would be 2 and 3. The numbers 2 and 3, and to make it a -1, it would need to be 2 minus 3, and I could check it. 2 times -3 is a -6. So those would be my two numbers m and n, such that they multiply, or the product is the value a times c, and their sum is the value b. So what does that mean? Well, the next step is we took a and we'd split its power, and we put this in parentheses. So if you split the power of it squared, you get just the power of first, x plus 2, plug in the value m, and then I again split the power. I'm splitting this power right there, and I would get x minus 3. That's going to be my numerator. So that's what we just came up with, and now what I'm going to do is slide this over a little bit and say this, all that is my limit here. as x approaches 3 of this. But we can see algebraically that I could simplify that limit by canceling those out. We called that earlier this school year a removable discontinuity. It's where we got a hole in the graph. And so it looks like now we're just finding the limit as x approaches 3 of x plus 2. And that's quite simple. We can use direct substitution and just say, okay, well, that will be equal to 3 plus 2, which is 5. And so now that we know our limit, let's check it out. Here's the picture of the graph. And you can see as you approach 3 from both the left side and the right side of the graph, the y value we approach is 5. So as we approach this value 3, as we close in on the x value 3, the function itself, or the limit, is approaching the y value of 5. And so that would be our answer. So the limit, we could say that the limit, and I'm just going to call this, for being shorter, I'm just going to call it f of x. The limit of f of x equals 5. And the reason I'm calling it f of x is because that's what they called it right there. So we used factoring to simplify. So we could use direct substitution, even though originally we wouldn't have been allowed to substitute. So the same thing here. Let's test it. If I did a direct substitution, I can say that this, since this is a rational function, polynomial over polynomial, I could say that it will be equal to, if I substitute that -2 in, -2 plus 2 divided by, which is going to be 0, divided by -2 quantity squared plus 2 times -2 squared minus 3 times, oops, I forgot the -2 minus 6. So what I have here is I will have 0 divided by -2 times -2 times -2. That's 3 negatives. It'll remain negative. 2 times 2 times 2 is 8. So -8. Plus here, -2 times -2 is +4 times 2 is 8. Minus 3 times -2, which will be a +6. Minus 6. You might notice this time, the 8 simplify, 6's simplify, which leaves us with nothing on the bottom. And that we can't, there's no limit there. That's undefined. So we have a problem. Well, let's try factoring. If we wanted to try to factor, what I'm going to do is factor this by grouping. So this was just using direct substitution here. So what I'm going to do is try to factor this by grouping. So at this stage, I'm going to slide this down. Oops. And so if I graphed by, or if I factored by grouping, what I'm going to do is I'm going to look at these two groups individually and say, okay, what's shared in the front group? They both have a GCF, a greatest common factor of x squared. So if I pulled those out, it's kind of like a reverse distribution. If I pulled those out, I'd be left with an x in the front. X cubed divided by x squared would be x. And then 2x squared divided by x squared would be 2. Now, we can factor by grouping if it turns out that we have a shared factor over here. As I look, they both share the value. A 3 can go into both of these, and this middle symbol is going to fall straight down. So I'm going to factor out a -3. Factor out a -3, I'm left with an x. -6 divided by -3 is a +2. These two factors are shared. If they do share, what happens is you can rewrite this limit in the form, we had x plus 2 up top. I'm going to put it in parentheses for now. Since these are shared, what this means is x squared is multiplying times x squared, and -3 is multiplying by x squared. X squared is multiplying x plus 2, and -3 is multiplying times x plus 2. Since that's a shared factor there, we could rewrite it as saying the values x squared and -3 are going to multiply, parentheses means multiply, times the factor x plus 2. Now that I have it in this form, I can see that I could simplify those two factors. And so this would equal the limit of, since there's nothing left over on top, that's like anything divided by itself, though I simplified it with a line, technically is 1. Anything divided by itself is 1. Think about 5 divided by 5, 10 divided by 10, 11 divided by 11. It's always 1. So it's not a 0 here. It's a 1 over x squared minus 3. So that's going to be the limit that I'm using direct substitution on. So at this stage, I will say that's 1 over direct substitution here, negative 2 squared minus 3. And that to me looks like we're going to have negative 2 times negative 2 is 4. 4 minus 3 is going to be 1. The answer is going to be 1. So the limit as x approaches negative 2 of all of this that we had earlier, x cubed plus 2x squared minus 3x minus 6 is going to equal 1. 1 over 4 minus 3 is 1. Now let's graphically go take a look at this picture, because that was quite a problem there. If we wanted to look at this, f of x equals x plus 2 over x cubed plus 2x squared minus 3x minus 6. And we want to close out on the value negative 2. So we're looking at what's happening as we go to negative 2. We can see here that from the left side, so I've typed this in correctly, I'm seeming to get a graph that's not in agreement. Okay, I see what I'm doing wrong here. I was not looking, I was thinking negative 2 was where this vertical asymptote is. As I kind of look here closer, I see that negative 2 is not the asymptote is in between. That negative 2 value approaches the y value 1, which is exactly what we got here. The negative 2 as you approach it from the left, and the right side approaches this y value of 1. So that's correct. By the way, I want to show you this. We realized that when we simplified this function, we got 1 over x squared minus 3. So I just typed that in right here. And if you graph that, you'd see that it's the same graph. It's the same exact picture as before. The difference would be on the black one, if you highlight it, when you get to negative 2, it'll say undefined, because that's where we're dividing by 0. But on this simplified form, if I look at the red one, when you get to negative 2, you won't have undefined. It'll just give you a value, which is kind of skipping over. Let me zoom in a little bit. There it is. Negative 2, it gives me 1. So it's a little bit and kind of a neat trick there of, for that limit. All right, with that, I'm going to let you try one. If you need to pause the video, you can. But see if you can factor to simplify to come up with the limit. If you cannot factor it, then obviously the answer would be that the limit does not exist. All right, example 4 says use rationalizing. Now, typically when we think of rationalizing, we talk about rationalizing the denominator, that we're not going to leave a square root in the denominator. Well, here's a little trick that sometimes might occur when you're trying to solve for a limit. If I use direct substitution right now, we'd have a problem because I'd substitute and have a 4 in the denominator, and 4 minus 4 would end up meaning the entire denominator equals 0, and that's a problem. But see, what I can do here is when I realize I have a square root, well, we can take the approach of let's try to rationalize this value up top in the numerator. And the way that we learned earlier this year to rationalize is you multiply kind of by the opposite. It's technically called the conjugate. You multiply by the conjugate here. So if I have a square root of x minus 2, what I'm going to multiply by is the conjugate, which would be the square root of x plus 2. What this will do is create a perfect square in the numerator. Okay, so that's what I'm multiplying by. I'm multiplying top and bottom by the same value, which means I'm ultimately multiplying this equation by 1. So I'm not going to change the problem. So I'm just multiplying by 1. It doesn't change the problem at all. But instead of saying, okay, well, this simplifies with this, well, that's true. They do simplify. What I'm going to do is multiply across. And so whenever you have this setup right here, it's called the difference of squares. What's going to happen, it's going to create like this perfect square when you have x squared, or excuse me, square root of x times the square root of x. You get the square root of x squared, which happens to equal just simply x. That's the square root of x times the square root of x is x. And then you have the square root of x times 2, which would be plus 2 square roots of x. And then you have a negative 2 times the square root of x, so minus 2 square root of x. And then a minus 2 times a positive 2, which is going to give me a negative 4. In the denominator, I'm actually not going to multiply this value at all. I should have had a parentheses around that, forgive me. So I'm going to leave this as x minus 4 times the square root of x plus 2. And so what can I see that happens? Well, I have an x plus a square, 2 square roots of x and minus a 2 square roots of x. And all of a sudden my board went going really slow. Let me see if it'll catch up with me. So we need to simplify these values out. Sorry, I don't know what's going on here. Let me try. This value would simplify out with this value. And so now I can see that not only can I say those values will simplify, but now I have an x minus 4 and I have an x minus 4 here. And so I could actually cancel out this factor x minus 4 with this factor of x minus 4, which leaves us with 1 over the square root of x plus 2. And so how can I solve this limit from here? Well, we can now use direct substitution. So I would just simply plug in a 4 into my square root. So I have the square root of 4 plus 2 in my denominator. And so the square root of 4 we know is 2. And so I'm looking at having here 1 divided by 2 plus 2, which is just going to be equal to 1/4. That's going to be my limit on this particular problem. When I look at this graph here, as I close in on the x value of 4 from the left side here, the limit as x approaches 4 from the left, and as the limit of as x approaches 4 from the right, from the positive side, the y value we're approaching is, according to the graph, 0.25, which is 1/4. So now I'll let you try this one again. What you're going to need to do here is multiply by the conjugate, which would be the quantity of the square root of x plus 1 here. All right, now let's take a look at example 5 here. It says limits of power functions at infinity. So if we're looking at a function that has an even power, and then we have an even power, what happens is if you look at the limit as x approaches infinity, it will be going up to infinity. And if you go the limit as x approaches negative infinity, the function will also approach positive infinity. Why? Because an even power, if you approach infinity, will be infinity on both sides. It'll go, as you go right forever, it'll go up forever. As you travel left forever on this function, it'll go up forever as well. And it'll increase without bounds. So that's why if it's even and you're taking the, if your power is even and you're looking at the limit as x approaches infinity or negative infinity, you will have the solution positive infinity. However, if you look at a negative power, it'll make an S-curve, which means as you go left forever, it'll go travel down forever. Or as your x increases forever towards positive infinity to the right, it'll also increase to the right. And so that's if it's odd. So now let's take a look at this idea. It says here that if p be a polynomial function that's written in standard form here, then the limit of this polynomial function p will be the same as the limit of the greatest power, the leading term, and which we've kind of learned about this in way back when in lesson, 2.4, 2.3, something like that, chapter 2, way back when. All right, so here, if I'm trying to solve for this limit here, what I can do is I can say that the limit of this function here will be equal to the limit as x approaches negative infinity of the leading term, which the leading term happens to be 2x to the 4th power. And any graph or any function that has an even power means it'll be kind of parabolically shaped, at least it's in behavior. And so as we go left, we can see that this graph does go up forever. So the answer would be infinity. So this limit will be the same value, the same answer as this limit here. I guess I could write it all in. Now that does not mean that 2x to the 4th plus x cubed minus 7 equals 2x to the 4th, but it does mean that the limits will equal one another. The limit of this function will equal the limit of the second function I wrote here, the leading term. Those two would equal each other, which does equal positive infinity because the graph looks parabolic. Looks like a parabola. Okay, on part B, this limit right here would be equal to the limit of the leading term as x approaches a negative infinity of the leading term. The leading term is the highest power term, which is x to the fifth. Now x to the fifth, since it's odd, will be shaped like an S curve. And so as we go left, this function goes down forever without bound. And so the answer would be negative infinity. What am I doing? Negative infinity. As the graph travels to the left, the y values fall. As x values go left towards negative infinity, the y values fall without bound, so they approach negative infinity. Here's another one. As we look, as x approaches positive infinity, this would be equal to the limit. Again, not to say this function is equal to the function, what I'm about to write for the leading term, but the limit itself will be equal. This limit and this limit will be the same of the leading term. The leading term is x cubed. So again, I'm looking at a graph that looks like a S curve. And as I travel right forever, the graph increases without bound. So the answer here would be infinity. That would be our answer to this graph here, or to this limit. And so now here's one for you to try. Pause the video if you need more time. Now let's take a look here at example 6. And so on example 6, here's some rules that are showing you of rationals, how the limit will work when we approach positive and negative infinity. We gave these rules in lesson 2.5, and you might remember that we have 3 rules, and the rules that as we described them in acronym form or EATS-DC, that if the exponents are the same, you will divide your coefficients. It's the horizontal asymptote. It's the same rules for your limit as you go to the right and the left will be your asymptote rules. So where we had exponents are the same, divide coefficients. That'll still be true. If it's bigger on the bottom, then it'll be 0. Bigger on bottom, y equals 0 was our asymptote rule for in behavior or limits. It'll just be 0. And then if it's bigger on top, there was no horizontal asymptote. But for us, you could say bigger on top, it'll either be positive or negative infinity. So I'll just do big bot plus infinity. So that these are going to be our rules. And so the power is the powers and the fraction are the same. You'll divide your coefficients. If it's bigger on bottom, it'll be 0, and if it's bigger on top, it'll be plus or minus infinity, whichever, depending on the direction here. So as I look at this one, the powers of this rational function are the same. The exponents are the same. So I will divide my coefficients. This was all on lesson 2.5. Let me write that in the notes. Lesson 2.5 here. So I'm going to divide my coefficients. So this limit here will be 2/3. The limit as x approaches negative infinity of 2x plus 1 divided by 3x minus 4 will equal 2/3. And so as you see this graph, it has a 1 there. It shouldn't. This graph itself, as you go left forever, as you travel left forever, you'll see that there is this asymptote on this graph, and it's below the value 1. So 1 is actually not a good answer here. It's actually approaching this value of 2/3. That's the value right there that this graph, as you go left forever, is approaching. So 2/3 would be our solution here. Part B, I look at and I see that the power is bigger on the top. This one's bigger on top. So if it's bigger on top, I'm going to say the answer is going to be plus or minus infinity. Now, how do you know? This one is typically going to be viewed as if this is a shortcut here. But if you divide your leading terms, 2x cubed divided by 3x squared, and specifically ignore the coefficients, I'm going to say that's roughly going to be 2/3. I said ignore my coefficients. I just wrote them. 2/3 to the x1 power. I shouldn't even say approximately because that's not true. So I'm just going to do one little squiggly line. Now this function, if you plug in a positive infinity, that's going to look like a line. And so if you think of a line, and we want to know as we go right what's happening, the value is going to increase to positive infinity. So I'm going to go ahead and estimate that this increases to positive infinity, but let's go ahead and see it as a graph. So if I wanted to look at 2x cubed minus x squared, x squared over 3x squared minus 1. And as you zoom out, you'll see that it does look somewhat like a line here, which means that as we go right forever, it does increase forever to positive infinity. Now let me put in the line 2/3 x. When I divided by the leading terms, I got 2/3 x. Wow, look at that. It's almost as if math works. Oh, it does. Math does work. Math is a truth teller. It tells the truth. That works. So yeah, it approximately is 2/3 x. And so as we go right forever, as this graph goes right forever, that's not what I wanted to do. Let me try this again. Right forever, the y's go up forever. And that's kind of the pattern there. So now let's see this one. I'm looking at the leading terms. It looks like here's my leading terms right there. So this one, the exponents are the same. Exponents are the same. So what we'll do is we'll divide our coefficients. So the answer is actually going to be 5/2. So all this would equal 5/2. Let's check just to make sure. 5x cubed plus 2x squared minus x plus 1 over 2x cubed minus x squared plus 3x minus 2. As we want to see the graph as it goes right forever, I can see it's approaching a constant number. And if I put in 5/2, y equals 5/2. If I put that in and zoom in, you'll see that these lines are basically one on top of the other. There is very little difference. And the farther right this graph travels, the more and more true this would be. Let me go x value to. Okay, now that I'm way out here, let's zoom in. And so the closer and closer I see, or the farther and farther right I go, the closer and closer these two graphs will appear. And you can see I am so far in line here that they don't even show me another value on the graph. Like they're not even labeling this anymore. Kind of gives you an idea how close together those values are. So the answer would be 5/2 here. So here is one for you to try. All right, example 7, limits of sequences. Let's say on part A, it wants us to find the first 5 terms, remember this from chapter 10, of this sequence, then find the limit of the sequence as it exists. So the limits here are going to work the same way as the rules we just used. So I'm going to kind of go out of order here. I'm going to first find the limit. If you were talking about the limit as n approaches infinity, let's just say as it goes right forever, of 2n plus 3 over n plus 4. You might be saying, why am I using n? Well, because the function itself uses n. Well, what you would do is you treat the same rules and you'd say, okay, the exponents are the same. They're both the exponent of 1. So it'd be you divide your coefficients, which in this case would be 2 divided by 1, which equals 2. So the limit's going to be 2 here. But to find the first 5 terms, if you remember this, what you do is you would just call it A1 for the first term and you plug in a 1. So 2 times 1 plus 3 over 1 plus 4. And we would find that the first value, 2 times 1 is 2, plus 3 is 5, divided by 5. 1 plus 4 is 5 equals 1. So A1 is 1. The second term, A2, would be 2 times 2 plus 3 over 2 plus 4. 2 plus 2 is 5. Excuse me, 2 times 2 is 4 plus 3. is 7. 2 plus 4 is 6. And so we get the value 7/6. All right, the third term would be 2 times 3. Since n is now 3 plus 3, that's 6 plus 3 is 9 over 3 plus 4. So like I said, 2 times 3 is 6 plus 3 is 9. 3 plus 4 is 7. Okay, we got 2 more terms to find. The fourth term, 2 times 4 plus 3, that's 8 plus 3 is 11. And then 4 plus 4 is 8. 11 over 8. And then finally the fifth term, 2 times 5 plus 3 over 5 plus 4. 2 times 5 is 10, plus 3 is 13. 5 plus 4 is 9. And so what's happening is we start off with the value 1, and the function each time is getting a little bit larger and a little bit larger. And you'd think that might go on for infinity and just keep getting larger and larger and larger. But the truth is it doesn't. It actually is going to approach the value 2 here. That as we go right forever, this will close in on the horizontal asymptote of y equals 2. These arrows are a little bit off. So as x goes to positive infinity, as we approach positive infinity, the graph itself would approach the y value of 2. So that's what the answer would be on this one. So the first 5 terms, 1, 7/6, 9/7, 11 over 8, 13 over 9, and so on. And the limit would be 2. And that would be my solution to part A here. Now part B, it says find the first 5 terms of the sequence, then find the limit of the sequence as it exists. Okay, and so this time we're in factored form across here. Now I could simplify this. I'm just going to make my whole equation a little bit easier. I'm multiplying by 3 and I'm dividing by 9. I can change this to a 1/3 because 9 is 3 times 3. So 1/3 in the numerator and 1/3 in the denominator will simplify. And this one, I can't just say cancel those ends because you need to FOIL that out or multiply and distribute all that out first. But I can from here determine that ultimately the leading term would be n squared, and this would be 3n squared when I multiply across. So 1 times n, giving my lead term of n squared. And down here, n squared times 3 would be 3n squared. So that means my limit here, the limit of bn as n approaches infinity, I'm just going to call that bn, will equal 1/3 because the exponents are the same. Exponents are the same. You're dividing coefficients, and so it'd be 1/3. Now, with that, let's find the first 5 terms. So b1 would equal, if I plug in a 1 across, it would be 1 plus 3, which is 4, times 1 plus 4, which is 5, over 1 squared times 3. So 4 times 5 is 20, divided by 1. 1 squared is 1, times 3 is 3. It's 20 over 3. That's the first term. B2, let's see, we plug in a 2. We have 2 times 3, or 2 plus 3 rather, that's 5, times 2 plus 4, which is 6. So 5 times 6 is going to give us 30, over 2 squared, which is 4, times 3. 4 times 3 is 12. And that could be reduced to 15 over 6, which actually reduce, let's see, a bigger number goes into those. So instead of dividing each by 2, since 3 goes in it, let's divide each of these by 6. 6 goes into that 5 times, 6 goes into 12 twice. Okay, so it's 5 over 2. The third term, we'd have 3 plus 3 times 3 plus 4. So 6 times 7 is going to equal 42, over 3 squared, which is 9, times 3 more, which is 27. 3 goes into both of these terms. 3 goes into 42 14 times, and 3 goes into 27 9 times. So it'd be 14 over 9. Fourth term, 4 plus 3 times 4 plus 4. That's 7 times 8, which is 56. Over 4 squared is 16 times 3 is 48. These could be reduced. I believe 4 goes into both of these numbers. 4 goes into 56 14 times. 4 goes into 48 12 times, which means I could have divided this by 8. 8 goes into this 7 times. 8 goes into 48 6 times. 7/6. And now last term, the fifth term, 5 times 3, or 5 plus 3 times 5 plus 4. That's 8 times 9, which is 72, over 5 squared is 25 times 3 is 75. So we're finally now underneath 1. 3 goes into both of these numbers. 3 goes into this 24 times. And 3 goes into 75 25 times. And so these would be my first 5 terms, 20 over 3, followed by 5 over 2, 7 over 6. Did I skip one? I skipped 14 over 9. 14 over 9, 7 over 6, and 24 over 25. And this is value are going to approach, ultimately is going to approach 1/3. Let me draw that there, semicolon a little bit clearer. So that's what we're ultimately approaching. The limit would be 1/3. We could graph these if you wanted to get an idea of what it's approaching. And you could look at the graph as well, but you will see that it's 1/3. Now here is one for you to try. Pause the video if you need more time.